Hello, I'm Oliver Chan. Today I will present to you a bibliographic review on remote sensing and GIS. I'll cover the main sensor types, key applications, common data errors, and correction techniques. Remote sensing is defined by NASA as the process of obtaining information about an object from a distance. According to the U.S. Geological Survey, it involves detecting and monitoring the physical characteristics of an area by measuring its reflected and emitted radiation from a distance. Another definition describes remote sensing as the science of acquiring information about the Earth using instruments that are not in direct contact with the surface, typically from aircraft or satellites. Once acquired, remote sensing data must undergo preprocessing to ensure accuracy and usability. This report provides a structured overview of the main remote sensing methods applied in geographic information systems, GIS, including optical, radar, lidar, and hyperspectral imaging. Remote sensing supplies timely, large-scale Earth data that GIS alone cannot. Our goals are to summarize the principal methods, show how they're used in GIS workflows, then discuss how to ensure data quality. This presentation provides a structured overview of the main remote sensing methods applied in geographic information systems, GIS, including optical, radar, lidar, and hyperspectral imaging. It examines key application areas such as environmental monitoring, disaster response, urban planning, and agriculture. Additionally, it analyzes common sources of error in remotely sensed data and outlines essential correction techniques to ensure data reliability and accuracy. The objectives of this review are: survey sensor technologies, illustrate GIS applications, identify errors and correction methods. Remote sensing systems are divided into two groups based on separate technical solutions. Passive remote sensing systems measure existing radiation such as the reflected solar radiation from the Earth's surface, and active remote sensing systems emit radiation on the study object and measure the reflected amount of radiation. In order to understand the difference between passive and active sensors, we can make this example. Ordinary camera is an example of a passive remote sensing system using existing light as input and forms an image on the film. If a flash is added to the camera, it becomes an active remote sensing system. Passive measures existing radiation while active emits energy and measures echo. Passive sensors like Landsat and Sentinel-2 capture reflected sunlight, and active sensors such as SAR, Sentinel-1, and LiDAR emit their own signals that can be microwaves or lasers to probe the surface. Optical remote sensing relies on sensors that detect electromagnetic radiation in the visible, near-infrared, and shortwave infrared regions of the spectrum. The visible range captures true color imagery. Near is effective for evaluating vegetation health. SWIR offers information on soil moisture, mineral composition, and vegetation water content. Landsat 8 and 9 offer 30-meter spatial resolution for most bands, and revisit the same location approximately every 16 days individually, or every 8 days combined. Sentinel-2, with its twin satellites, offers 1060-meter resolution across 13 spectral bands, and revisits locations every 5 days. On the other hand, hyperspectral imaging acquires data in hundreds of narrow, contiguous spectral bands, enabling precise identification of surface materials through their spectral signatures. While offering superior detail, hyperspectral sensors are complex and require greater storage, processing power. Synthetic aperture radar is an active remote sensing technique that uses microwave energy to image Earth's surface. SAR penetrates clouds and works at night, perfect for flood, deformation, or marine monitoring. Sentinel-1 includes two C-band SAR satellites operating at frequencies between 4 and 8 GHz. It supports multiple imaging modes. Our AEDAE-SAET2 also uses C-band SAR and supports imaging under any atmospheric condition. It produces thousands of images annually and supports applications such as ice monitoring, marine surveillance, disaster response, and environmental assessment. LiDAR, light detection and ranging, is an active remote sensing method that uses laser pulses to measure distances to Earth's surface. It emits rapid laser pulses, calculates the two-way travel time of each pulse, and determines distances based on the speed of light. These measurements, combined with GPS and IMU, inertial measurement unit, data, generate highly accurate 3D models known as point clouds. The integration of remote sensing data into geographic information systems is essential for monitoring land use, and land cover changes across spatial and temporal scales. Remote sensing supports disaster management at all stages, from early warning to response and recovery. GIS platforms integrate remotely sensed data, optical, radar, and thermal, with ancillary spatial data such as topography, infrastructure, and population density to inform decision-making. Remote sensing provides critical data for agriculture, including crop health, growth stages, and yield forecasting. Vegetation indices are used within GIS to detect plant stress and optimize inputs such as irrigation and fertilizers. High-resolution imagery supports monitoring of urban growth and updating of land use maps. LiDAR provides detailed 3D representations of buildings, transportation infrastructure, and urban features essential for smart city planning. However, raw data contains errors. Geometric distortions shift pixel positions, atmospheric effects add haze, and radiometric inconsistencies arise from sensor calibration and noise. Geometric distortions refer to spatial inaccuracies in remotely sensed imagery that alter the true position, shape, or size of surface features. These errors stem from multiple factors including sensor optics, platform motion, terrain relief, and the Earth's curvature and rotation. As electromagnetic radiation travels from the Sun to the Earth and back to the sensor, it interacts with atmospheric gases and aerosols, causing scattering and absorption that degrade image quality. That's what we call atmospheric interference. Radiometric inconsistencies are variations in pixel intensity, values unrelated to actual surface reflectance or emission. These errors may be caused by sensor malfunctions or calibration drift, and manifest as random noise, stripping, banding, or missing data lines. Geometric correction techniques are applied to ensure that each pixel corresponds accurately to a ground coordinate location. Image registration aligns a target image to a reference image or map layer. Orthorectification extends this by correcting terrain-induced distortions and sensor viewing geometry. Atmospheric correction techniques reduce the effects of atmospheric scattering and absorption on image quality. Radiative transfer models simulate the interaction of electromagnetic radiation with the atmosphere. Alternative image-based methods provide effective corrections without relying on external atmospheric data. Radiometric calibration converts raw digital numbers into physical units such as radiance or reflectance, enabling quantitative analysis across sensors and dates. Radiometric normalization techniques further adjust multi-temporal datasets to eliminate inconsistencies not related to surface change. Remote sensing is a fundamental component of modern geographic information systems, GIS, enabling the acquisition and analysis of spatial data at multiple scales. Through optical, radar, LiDAR, and hyperspectral imaging technologies, it is possible to monitor land use, manage natural resources, support disaster response, and assess environmental conditions with increasing precision. However, the accuracy of remotely sensed data depends on careful preprocessing and correction. Geometric, atmospheric, and radiometric distortions can significantly affect data quality, making correction techniques essential for reliable analysis. As remote sensing technologies continue to evolve, their integration with GIS will play a pivotal role in addressing global challenges related to sustainability, urban development, and climate monitoring.